So now in this video we're going to make a Schmitt trigger demonstration circuit with the 555 timer. And we're going to use a 555 timer in a dual inline package. That's all I use for integrated circuits right there. But in any case, usually they got an indication of where the top is, maybe an indent there or an indent right there. But you start to the left and go in counterclockwise. You number them. So 1, 2, 3, 4, the pins right there. And we get to the bottom and go across 5, 6, 7, 8. Some integrated circuits are longer. You just keep numbering down before you jump across until you get the total number. So in any case, we are going to use the NE555 right there. It may even have a letter after it. It may have P or something. But in any case, NE555. There's also a UA555. That's actually micro, but sometimes they'll say UA555, LM555. A lot of different 555s, but NE is the most common, and so generally I assume that's what you're going to be using. But consult the data sheet for the specific 555 timer you're using. Basically they operate the same, but maybe they can handle more current, more power, maybe less current, less power. There's advantages and different disadvantages for each one for the most part. So here is the pin layout. So we have to power the integrated circuit. So that's VCC, the positive supply. That is ground. In this video, we're going to focus heavily on the trigger and the threshold. They look at the voltage, and that's being input to them, and the output will respond in some way or another. We'll look at that coming up. The output provides power to a load, either sinks or source current. Now we have the reset pin. We're going to disable it. If you reset it, I think it holds the output low no matter what you do. And then control pin, we're not going to worry about that right now. So here is the schematic diagram for the circuit we're going to do. As I said before, pin 6 threshold, pin 2, they're going to monitor a voltage. We're going to use a trimpot to change that voltage. So we can go all the way down to 0 volts, or if we use a 6 volt power supply, you don't have to use 6. 5 will work exactly the same in the circuit, except for the voltage will be slightly different. But we could go up to 6 or down to 6. It's a trimpot, a potentiometer, wired as a voltage divider right there. So what happens is, if we go down below 1/3 of the supply voltage, so remember we got pin 8 positive supply and pin 1 to the negative supply. If we go below 1/3 of the supply voltage, the output will go high. So it'll connect to 6 volts as good as it can. The red LED will light up in the circuit. Pin 3 was the output, remember. So it doesn't get all the way to 6 volts, but it'll get as close as it can right there. And then if we raise the voltage, once we get up to 2/3 of the supply voltage, the output will be low. And that means it's connected to ground as good as it can, which it does pretty good. Going to ground. The NE555 gets really close to 0 volts. You know, not exactly, but pretty close. So we wire up the blue LED so it lights up when the output is low. I like that color coding scheme. So now in between 1/3 and 2/3 supply voltage, this is why it's a Schmitt trigger. And actually it's an inverter too. And so you can see when we go up to a high enough voltage, the output is low. When we go down to a low enough voltage, the output's high. That's an inverter, and it's the opposite of the signal when it comes to high and low. Now, between 2/3 and 1/3 supply voltage, that middle ground, it stays either high or low, whatever it was last put into. You have to go a little extra to switch it, and so that middle ground between 1/3 and 2/3 is called hysteresis right there. So internally, inside the 555 timer, you have a voltage divider. 3 equal value resistive areas. Some people say it's 5K each, which is where they say the 555 comes from. So I don't know about that, but in case, that's what they claim. Now, pin 5, it's the control pin. You can actually adjust those voltages a bit, as you can see here. So it taps into there. You can add resistance in ways to change those voltages, but we're just going to leave it floating. Some people take a capacitor and put pin 5 there. They put a little capacitor to ground. We're not going to do that. We're going to keep this simple. So in any case, that really explains the circuit pretty good. Blue LEDs are naturally brighter, so I have a higher value resistor, 1 kilo ohm, to limit current a bit more. Red LEDs not as bright, plus we're going to lose a little bit of voltage from the positive supply, and so we're going to use 220 ohms to get more current going through it, but the LED should be relatively close in brightness. So as I said before, look at a data sheet for the particular NE555, or particular 555 I mean, that you're using. We're going to use NE555 here. In fact, probably any 555 timer will work probably about exactly the same for this particular circuit, but other ones may have different needs that cannot be met. So for one thing, this can work according to the data sheet. It's recommended 4.5 to 16 volts, and so at least 5 volts probably you'd want to use. And we can sync or source, so current, when it's syncing, it's going that way. When it's sourcing, it's going that way. 200 milliamps, so quite a bit with the NE555. I have another type of 555 timer that gets to the supply voltages better at the output, but cannot provide much current at all. And so that's one thing to look for. But the NE and the UA, I know, micro A, they can handle quite a bit of current. And so, as I said before, low level, it gets, according to the data sheet, probably about 0.1 volts from ground there. So pretty close to 0 volts, but not quite, maybe 0.1 volts. And it might even be 0.35 volts, but gets pretty close to ground. Now, when it comes to the high output, so at 5 volts, and I think it gets worse as current goes up, but it's talking about 100 milliamps of current. They got negative 100 milliamps for some reason, and I would think that would be positive, that would be negative, but in any case, 100 milliamps. Well, it is, so it's high sourcing current. You can expect maybe only 2.75 volts coming out, but typically 3.3. So I don't think it's as bad at low currents, but you lose quite a bit of voltage. That's from 5 volts right there. So we'll probably have at least 4.3 volts, maybe slightly higher when the output's high for this particular circuit. So, in any case, the internal resistors, I forgot to mention there, they set the 1/3 supply voltage and 2/3. That's how the integrated circuit knows 1/3 and 2/3 internally, and as long as we don't adjust it with 5. And so when it comes to the inputs, that's how input 6 knows when you've exceeded 2/3 voltage, and pin 2, the trigger pin, knows when you dropped below 1/3 of the supply voltage. So here we are on the breadboard. There's an NE555 timer right there. So to begin with, we have to power it, positive to pin 8, as we said before, negative to pin number 1 over there. Pin number 4, that is the reset pin. It's waiting for a low voltage. I think it's less than half of the supply voltage. But in any case, we're putting it to the positive supply. That's the full supply voltage. That tells it not to do anything. That's very important. There's pin 5, the control pin again. We're just going to leave it floating. There's also a discharge pin. That's for discharging capacitors for the most part. And so we're not going to use that in this video right there. So that's pin 7. Now we got 6, the threshold pin. Pin 2, the trigger pin. For this circuit, they're looking at the same voltage right there. And anytime you want it to respond to a voltage, generally speaking, either setting the output high or low, you typically tie those two together, not always. So again, it's looking at the voltage. We're coming up to here to the middle of the trim pot. So I really like this trim pot. It has these little wires, fit pretty nicely into the breadboard right there. The two end pins, they are a resistive element. There's a resistor basically going across there. Here is a wiper. It taps in. So you saw with those fixed resistors in the schematic, we had 2 points we could go to. Now we have any point along the resistive element where we got some of the resistance towards negative, some of it to positive. So there's a little negative, a lot positive. Now we get rid of all the negative resistance, and so a direct connection to ground. A lot of resistance positive, and we can do the opposite. So that's why we got 6 volts up there, about 4 volts there, about 2 volts there, and about 0 volts there. The voltages of interest in here, and we can go anywhere in between. Right there is about 3 when we got it set to 6 volt power supply. So now for the LEDs, again, the blue LED I want to light up when the output is low. So I'm going to put the long lead, the anode, up here, short lead, the cathode, down in one spot, and a 1 kilo ohm resistor, as we said before, from the cathode to the output. So current will flow this way, positive if we follow positive and negative through the LED, and then to the output, and then the output will be connected to ground. Pretty good, as I mentioned before. So those are voltages that you can measure if you really want to. Red LED, we're going to come down here, line lead the anode up one spot, short lead the cathode down one. We got to the jumper there. Again, the order of the LEDs and the resistor doesn't matter. Sometimes I have from the output showing the LED to resistor, but resistors are more flexible than LEDs for putting on the breadboard. So order doesn't matter as long as the LED is in the right way. So we got the LED down there. So that is it for the circuit. I will quickly grab the alligator clips right here and connect them from the power supply, and that shouldn't take too long, so I'm not going to cut. Just going to keep shooting. The power supply output is off. It's not providing power. Now it is providing power. So we have a blue LED lit up. We're in the hysteresis range with the trim pot. We are halfway. So we know that the output is low, and so it considers that we had a high input for the most part. But we're halfway, and we're in that hysteresis range. So if we want to set the output high, as I said before, we have to turn the voltage of the trim pot down below 1/3. There we go. Now we have it high. So that's what it's telling us. That's what I'm reading from the circuit. Now we got to go back through that hysteresis range to 2/3 of the supply voltage, which would be 4 volts with a 6-volt power supply right there. So I was thinking of using an oscilloscope to take those measurements, but this video is long enough, so hopefully that was good enough. I'll do oscilloscope measurements of later videos. But for now, I think that's a good continuation for this course. This is part of the course that I'm doing, the most recent one, so hope you enjoy. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help a lot. I would really appreciate that. I'll see you in the next video.